Hey everybody, we're going to finish up with HPLC as our last type of chromatography. So if you recall, a few minutes ago I was talking about GC, or if you might be watching this a few hours later, liquid chromatography is another choice that we might make for separating species from a complex mixture. And we choose liquid chromatography when the samples are a liquid and they're non-volatile. In other words, we can't get them into the gas phase. So liquid chromatography would be a possible choice for separations. And these are used in biochemistry. They're used in the pharmaceutical industry. Problem with liquid chromatography is that it's a little more expensive, a little more time consuming, a little more wasteful. Sometimes we're going to be using organic solvents that are kind of hard to dispose of. So we do have some issues that we might have to take into consideration when we're conducting these types of separations. So liquid chromatography, in this type of chromatography, the mobile phase is going to be a liquid. So remember, gas phase chromatography, GC, the mobile phase is what we use to determine the type of chromatography. So for liquid chromatography, the stationary phase is also going to be in a column, and it will also be a solid or a solid with a liquid support on top of it. The column is going to be a packed material, and normally what we want to do for these columns, we want to pack them with very small particles, and we get small particles, we get better efficiency. Remember the Van Deventer equation. The smaller the particles, well, one thing we're going to reduce is the eddy diffusion factor, the A factor. That's going to influence the smaller HETP, the height equivalency of a theoretical plate. The other issue about small particles, we get better mass transfer because there's a greater surface area of the particle that the liquid's in contact with. So there's better mass transfer, and that also reduces our height equivalency of a theoretical plate. And it results in a faster flow rate. We can run our experiments at a faster flow. The only problem now is we require a higher pressure because we have small particles. To get the liquid through there, we need to put a higher pressure. And this is where HPLC comes into play. Now, HPLC is known as high performance liquid chromatography. Some people also say it's high pressure liquid chromatography. That's essentially what we're doing. We're applying a greater pressure. The pressures that we're applying are up to about 1,000 ATM. And this results in higher resolution. We can use smaller particles, and it affords us a faster analysis time. So let's look at the instrument that we use for instrumental analysis. This is, if you take Chem 4230, you'll get to use this instrument. So first thing we need to do is to inject our samples. So let's show you what you guys will be working with. So here is our samples over here that we would use. And what's cool about our instrument, I'll take it apart a little bit to show you, is we have an auto sampler. Really cool. Right there, if you look inside there, this is an auto sampler tray. Now, the auto sampler allows us to put our samples on a tray, and what happens is we can put in up to 100 samples, and we can program our instrument to inject a certain amount of sample, and usually I think our programs are using about 5 microliter, pretty small amount of sample. And you know what? I had students that they would put like 20 samples in there, and each run took a certain amount of time. That's one thing. Some of the runs can take 15 minutes. And if you're running 10 samples, that's 150 minutes. which is like 2.5 hours. So what I had students told me they would do is they would program everything, put their samples on the auto sampler, and go home, and the next day get their data. So that was pretty cool. Auto sampler is really a nice way to run these experiments in terms of sample injection. Okay, now remember in gas phase, gas chromatography, we used a gas as our mobile phase. What we use for liquid chromatography is liquid as a mobile phase. Now, the liquids that we use are typically in reservoirs. We have one up here. This is methanol. And we also have an aqueous phase. And normally this is going to be a buffer at a particular pH that we run our experiment. So we have reservoirs with tubing that move into the instrument, and then a little further downfield, let's see if I can get this without breaking. Ooh, this is cool. So there's the inside. There's the inside of it. This is real cool. So there's the inside of the instrument. Over here, we have a pump. And the pump is what allows us to give us our high pressures up to 1,000 ATM. So there's our auto sampler down here, and we have liquids coming in from our wet reservoir to carry our sample to our detector. Now, the detectors that we use for liquid chromatography, as we said, are going to be most likely a UV vis. We can use other types of detectors that are also compatible. UV vis is a typical workhorse. Now, I really didn't get to show you the column because you were like, well, where's the column? There's our column right there. Columns. This one is about, I don't know how many centimeters. This is 15 centimeters long. These are normally anywhere from like, up to about 30 centimeters long in most cases. And these are packed with small, finely packed particles that are silicone particles, just like we showed earlier. The silicone can be functionalized, and that functionalization of the silicone can allow us to run a column that's nonpolar or one that's polar. And like we said earlier, we use the mode of chromatography to help us communicate what we're trying to separate, what the column's composed of, what components we expect to come off first. Now, if we pack this with particles that had silanol groups like we showed earlier, that's going to be normal phase. It's going to be a polar column, and it's a polar stationary phase. And normally, in these cases, no pun intended, we're going to run a non-polar mobile phase. Mobile phase is important in this case. Mobile phase helps to remove substances from our column. So now when we think about the strength of our phase, of our mobile phase, we can actually encourage the removal of substances better from our column if we change the strength of our mobile phase. I'm going to move over to the dry erase board and talk a little bit about normal phase chromatography real quick. Because the strength of the mobile phase, and you'll hear that term, you need to know what they mean by changing the strength. So let's remember normal phase chromatography. Silanol groups. That's big in normal phase chromatography. And remember, we call it normal phase simply because that was the earlier methods. Okay, here's our solid support. That's nice and easy to see. And the solid support has exposed SiOH, and that's what we mean by silanol groups. Here's our solenoid. And these are polar. This is more electronegative than our silicone. And there's also hydrogen bonding available in this situation. So let's run a solute through this column, this liquid. And it's running with a mobile phase that we would expect the mobile phase to be nonpolar. So this is normal phase chromatography. Normal phase, polar stationary phase. And what we would have for our mobile phase, so there's polar stationary, and we're going to run a nonpolar mobile phase. Okay, and now we're going to introduce a solute. Let's just keep it simple. Let's just assume we're putting one substance on this column. And we'll call this substance X. And X is polar. X is polar. So X likes to spend time on our column. We would run mobile phase through there. It doesn't like to spend a lot of time in the mobile phase, but it would equilibrate, and time would go on. It would move down the column a little bit, and then more time would go on, and it would move down the column a bit. And we would collect a chromatogram. Here's our response, and here's our time. Again, normally we're going to have multiple species, but just so you understand what I'm discussing here. And what we would find is that our sample X comes out down there. And if we had this on a time scale, what if we found out that this took 60 minutes? And you're working in the lab, you're a grad student or you're a researcher, and you're like, man, that took a long time to get that guy off there, and I got better things to do with my time. How can I reduce my run time? How can I reduce the time to get that polar substance off there? I can make this nonpolar mobile phase a little more polar. In other words, I can increase the strength of it. When I say increase the strength, I'm making it more similar or stronger like our stationary phase. So if I make the nonpolar mobile phase a little more polar, so we're going to make this more polar. A more polar mobile phase. Now, in this situation, what we're saying is we're making it stronger. Let's see what happens in this situation. Remember, 60 minutes was about how long it took. Okay, we run this and we have X sticking. Well, now let's think our mobile phase is more polar. So now the mobile phase will want to interact with our stationary phase, and it'll kick out X a little faster, and X will move down a little quicker, and then the more polar mobile phase will kick X off again, and X will move down the column a little quicker. And guess what? When we're all done, we find that our sample comes off in 20 minutes. And that's because we made the mobile phase a little more polar. It's going to interact with our stationary phase, and sort of dislodge our species, to encourage it to get along its way and to come off the column. So that's what we would do in a situation in which we're running a normal phase chromatography. We also have reverse phase chromatography. And this is the more common reverse phase. This is used more often because most of our non-volatile liquids are going to be fairly non-polar substances. A lot of them are long proteins or other types of biochemical substances that we would use in pharmacy. Reverse phase. Reverse phase chromatography it's going to have a non-polar stationary phase. And it's going to have a polar mobile phase. So, a non-polar stationary phase is going to be really amenable to retaining non-polar substances. So we're going to expect those to come out later, and our polar guys are going to come out really quick because they don't want to stick to the non-polar stationary phase. Once again, how we functionalize these surfaces, these silicone surfaces, sometimes you'll hear the term, we decorate them. We do some chemistry on them. A common non-polar stationary phase, there's two of them. There's C8 and C18. C8, C18 is implying that we have this group on the silicone particle. So it would be silicone, C18. Well, guess what? It's going to have an 18 carbon chain. That's pretty non-polar, and that's really good at retaining non-polar substances. Now, the mobile phases that we use for our liquid chromatography, as we showed earlier, there were two reservoirs. If you remember what I showed a few minutes ago, we had two reservoirs. We had one that was methanol. We'll just call that A. And another was an aqueous phase buffer. The methanol is an organic solvent. Methanol is going to be less polar. So we'll say it's less polar. Aqueous buffer is composed of water. It's more polar. And what we do is we combine these through our tubing to flow in at different rates. And that is a way we can control the percentage of our mobile phase in terms of, is it a more polar or is it a less polar mobile phase? Remember, we showed a few minutes ago, if we change the strength of our mobile phase, we could encourage different substances to come off at different times and speed up our analysis. Now, one issue that we discussed earlier of improving our analysis, improving efficiency, improving our speed of our analysis for liquid chromatography is to use a radiant elution. Now, a gradient solution is the situation in which we change the composition of our mobile phase to encourage separation of different species that are either co-eluting in one condition or not separating completely. Okay, let's think about a situation in which we're doing a reverse phase experiment. Reverse phase is we're going to use a non-polar column. And we're going to look at our chromatogram. And there's what we get at the beginning of our experiment. We have 4 species. 1, 2, 3, 4. And they're in a reverse phase. They're on a non-polar column. And again, this is time. There's time. Okay. First question. Species 4 comes off at the very end. It's taking a long time. It's on the column for a real long time. What can you tell me about species 4 in comparison to species 3? Think about it. Take a minute. Stop. Okay, I'll tell you. Since this is a reverse phase, it's a non-polar column. Number 4 stays on the longest. Number 4 is the least polar of those species. It's the least polar. It stays on the column the longest and comes out at the end. Good? What can you tell me about 1 and 2? There's 2 things we should recognize. First of all, we're not getting good resolution. They're almost sticking together. And we can tell you another thing. They're both going to be fairly polar. Number 1 is the most polar. Number 2 is probably a little less polar than number 1. Got it? Makes sense? Well, how can we encourage this separation? One thing we can do is change the strength of our mobile phase. And this is what we do with gradient evolution. So, these 2 don't want to come off separately under our initial conditions. So why don't we change the strength of our mobile phase? Why don't we make our mobile phase, remember it's reverse phase. At the beginning, it's probably a fairly polar. Let's make it less polar. Let's make it less polar. If we make it less polar, well then maybe 2 will come off a little bit later. Okay. If we change the strength, we can do several things. We can change the polarity. What if we decided to make it more polar? Let's try that. Let's make this more polar. If this is more polar, one and 2 are staying on. 3 and 4 are getting kicked off pretty well. 3 and 4 are getting kicked off. Let's make our mobile phase even more polar. So let's make it more polar. And if we make it more polar, it might encourage 1 and 2 to separate a little bit better and really emphasize the differences in their polarities. Okay? But the problem is 3 and 4 are now going to stay on for a real long time because now we have a more polar mobile phase. There's 3 and there's 4. So this is using a more polar mobile phase. So you might say, we've actually reduced the strength. So what we do, and time takes too long. Too long. So what we do for a gradient elution is to gradually change it. So this is our gradient. This is our solution, a gradient elution. We might run, for the very first part of our analysis, a more polar mobile phase. We get one, we get two to come off. Then we change the flow. We start entering a less polar mobile phase and increase the strength in comparison to the more non-polar stationary phase. And then we encourage our less polar substances to come off. And using gradient elution, we can separate now the two polar species, change the composition of the mobile phase so it's less polar, and now we can do a nice separation in a time period that doesn't take too long. So that's what's important about being able to change the composition of the mobile phase. So the last topic, the final topic that we're going to discuss. So gradient elution is simply used to improve our resolution by changing the composition of the mobile phase over time and being able to encourage separation of all species. The last topic I am going to discuss is applications of chromatography. We can conduct qualitative and quantitative. I think this is a quant class, but it's important to understand a little bit about some qualitative features. So let's think qualitatively. Qualitative. One important thing that we need to know when we conduct an experiment is the retention time of the species. TR, that's the retention time. So sometimes the first thing we're going to do in an experiment is to run standards. Let's consider a case, and this is actually what we did in instrumental. We had students run samples, a sample that had a combination, and they tested it using HPLC. They do an HPLC analysis that has a combination of caffeine, benzoic acid, and aspirin. And they run their their analysis, their HPLC. I'm just going to make up some data here. And they get 3 peaks. There's three species in there. And let's just say this one comes out at 2 minutes, this one comes out at 4, and that one comes out at 6. So I actually do this with students, and I'm like, well, which one's which? How are we going to determine it? Now, this is HPLC. Boiling point's not going to help. If we looked at the structures of these 3 compounds, it's really hard to predict which one's polar and which one's non-polar, because we're conducting reverse phase. Just to let you know, this is a reverse phase experiment. First phase, non-polar column. Each of these are fairly non-polar. So what we would do in a real life setting is we would run caffeine separately. All by itself. And we find out that it has a retention time of 4 minutes. Under this condition, we run it at the exact same conditions. Well, that tells us when we run a mixture, since we're getting a peak at 4 minutes, and we're running samples that have caffeine in it, that's where our caffeine peak is at. We then run benzoic acid. Benzoic acid, I'll just call it BA. BA comes out at 2 minutes. And then I run my aspirin sample, and I find out that aspirin has a retention time of 6 minutes. So when we conduct an experiment, qualitatively, knowing what the retention times are really important when we look at a mixture. So that's important for qualitative. And it is important for quantitative. When we conduct a quantitative analysis, quantitative analysis. What's important in quantitative analysis, peak area, or some people do use peak height. Peak area is the better choice. Is directly proportional to the analyte's concentration. That's real important. So let's look at our analyte. We run a chromatogram. We get a nice looking chromatogram like that. Now, today we have programs that can calculate the area. If you were back in the 90s when I was there, you would have to treat that as a triangle, like we did. And then you would have to calculate the area of the triangle. And if you calculate the area of the triangle, that's proportional to the concentration of that sample. You know what else we did? We counted boxes on strip chart recorders. The strip chart boxes, I don't know if you ever saw those little graphs. That's the reason why they had them. You would count the boxes. The number of boxes was proportional to area, which is also proportional to the concentration of the analyte. So we did a lot of crazy things back then. But the peak area that we calculate is directly proportional to analyte concentration. So what we would do is we would create a calibration plot. And you would have your peak area versus analyte concentration. And you would prepare standards, just like we've been doing. You would prepare a standard that is 1 part per million, one that's 3 parts per million, one that's 5 parts per million, and one that's 8 parts per million. Again, just an example. You would run a chromatogram and get the peak area. What if this one had a peak area of 10? This had a peak area of 12. This one was 15, and this one was 20. You would create a calibration plot of peak area versus analyte concentration, generate your graph, and then you would take your unknown. Y would equal the unknown's peak area. What if this was 16? You would plug this into your equation, solve for x, and that would be the analyte's concentration. You guys have done that in a lot of the exercises that we've done in prior testing environments. So that's pretty much it for today. If you have any questions on any material at all throughout the semester, before the final, send me an email, send me a request. I'll make a video solving problems. I'm glad to help you. It's part of my job. We can't have office hours because of the situation. So think of an email as my office hours. Any questions, I'll be glad to answer. I did post some information about grading, both for the lecture and for the lab course. So feel free to send me emails for any kind of questions that you have. Good luck. It was great working with you, and best to everybody. Take care. Thank you. Oh, no. I think it's still there.